along.
There's a certain amount of overlap, actually, in what I want to say with Joel's talk previously, but I'm going to say it more from an atmospheric perspective, so maybe it doesn't do any harm to say things sort of a similar way, but from different perspectives. And also, I should say, I'm kind of going to present things in rather general terms, and my colleague Matt Chantry, who is after lunch, will kind of show you some specific details on what we're talking about. I've slightly changed the title from what's in the program, just to sort of focus on what I consider to be two important roles, not the only two important roles, but two important roles for weather and climate prediction. And yeah, so just to note that if you're not in the field, yes, we do use hierarchies of models, from very simple models to very complex models, but I'm going to focus exclusively in this talk on the complex models, in other words, trying to simulate Navier-Stokes and the associated PDEs of the comprehensive representation of the climate system. And, you know, these models are important these days. I mean, they've always been important to try to understand what's going on in the climate system. If you have something where you can represent everything in a satisfactory way, then you can start to take out processes and see what's important and what's not important. So that's clearly, you know, that's always been a kind of major goal for developing the comprehensive models. But these days, clearly these models feed into a number of policy issues directly. I say mitigation, but you know, an example is how much can we rely on wind energy over the UK and in the surrounding areas in 50 years from now? Are we sure the wind's going to blow as strongly as it does now? Are we sure we're not going to get more anticyclones, blocking anticyclones, which might reduce wind energy? So these are kind of critical questions. I mean, how's cloud cover going to change, which would affect solar energy? So these do have implications for mitigation. But perhaps, you know, central is the whole adaptation question, which my talk is largely predicated on. And related to that, you know, these days, every time there's a severe event, I'm sure you've seen in the media, there are certain statements trying to say how much of it was caused by climate change. And that's important because if you can associate these things with climate change, there's an implication, therefore, that these events will happen more frequently in the future. And, you know, people still talk about the plan B if we can't agree to cut emissions, which is, for example, spraying aerosols into the stratosphere to reduce sunlight. But that's a priori a bit of a dodgy thing to do because you're not really balancing. The problem with climate change is an increase in the trapping of infrared energy, and you're trying to balance that with a reduction in incoming solar visible and ultraviolet. So the two are not quite compensating each other from a radiative point of view. So can you be sure you're not doing anything untoward with, I don't know, monsoons or moisture flow into the tropical rainforests? So that's a question which you can only answer with models. I mean, you might think adaptation's an easy problem, but you know, think of yourself as prime minister or president of a country. What are you actually adapting to? Is it a world where you're getting more heat waves and droughts, in which case you'll need to, you know, make sure there's adequate water supply, and you know, invest in techniques to reduce heat stress and so on? Or is it a world actually where there are more storms and floods? Okay, well, you might say, let's just go to IPCC and they'll tell us what's relevant to our country. So, but unfortunately, you'll get a rude shock if you do that. This is from the sixth assessment report, showing changes in rainfall for two different scenarios in winter and summer. I think the thing that you can perhaps see most well, hopefully you can see, is a lot of the world has this kind of cross shading, and if you look at it, it says no or no robust significant change. In other words, the models just don't agree, even on the sign of the precipitation change. Now there are a few regions, particularly in winter, where there seems to be a signal where the models do agree. Is that a reliable signal? Can we trust at least the situations where the models all agree on a sign? Well, unfortunately, I would say no. And this is a paper which I wrote with the director of the Max Planck Institute, Bjorn Stevens. We published in PNAS. And the figure there is comparing the bias in the CMIP models on the left-hand side in terms of precipitation for three of what are considered to be the top, the most trustworthy of the CMIP models. And on the right-hand column is the kind of signal in terms of precipitation between the end of this century and the present day. So it's the climate change signal. And what you can see is that the bias is actually typically larger than the signal. Now we're dealing with clearly a nonlinear system, equations are nonlinear. So a nonlinear system which has a bias comparable with the signal you're trying to predict you're not in a happy place. One can think of many situations where a nonlinear system with a bias is of that magnitude would not predict the signal accurately. So for this reason, kind of mirroring what Joel has mentioned, there's a lot of interest in trying to see if we can do better. We know from numerical weather prediction, one very clear thing that has come out over the years is that improving the resolution of the weather forecast models has improved the skill of these models. And there's no reason why that shouldn't also be true for climate models. I mean, one can, itemize a few specific things. I mean, you're more accurately representing the underlying laws of physics. You're not having to rely on parameterizations for important processes. You're also representing things like topography and land sea boundaries more accurately. And in the case of topography, this is quite important because often mountain chains act as barriers to flow. The mountain chain might be relatively thin in the sort of flow direction, but as long as it's got enough height, it poses a barrier to the flow, and the flow goes round the object. Now, if you have a low resolution representation of that thin mountain chain, you'll decrease the height of the barrier, or decrease the height of the mountain chain, so maybe it no longer becomes a barrier. So that's pretty important. And if you can get down to kilometer scales, then you won't have to parameterize deep convection, which is a really important process in the atmosphere, particularly in the tropical atmosphere. And by implication, the extratropics, because the tropical atmosphere radiates Rossby waves into the extratropics, which communicate information between the tropics and the extratropics. You'll no longer need these parameterizations of subgrid topography, getting the parameterized effect of the mountains right, for example, through gravity wave drag. And some of these ocean eddies that we saw about in the last talk can be represented explicitly without parameterization. And, we hope that will lead to smaller systematic errors, that bias will suddenly start to drop so that it becomes small compared to the signal. That's the hope. There's no proof of that at the moment. But from a physical point of view, it sounds plausible. Better representation of extremes. We kind of know that from things like hurricanes. There's very clear evidence that ability to simulate hurricanes depends on resolution and other types of extremes as well, which I talk about but don't have time. Something that's not often made actually is that if you're making forecasts, whether it's tomorrow's weather or next season's weather, or even these sort of decadal forecasts of like the AMOC or whatever, they do depend on being able to assimilate observations. And it's more difficult to assimilate observations into a coarse resolution model than a fine resolution model. Because, for example, if you have an observation that is being affected by a big thunderstorm cloud that the model can't actually represent explicitly, you're going to make an error in assimilating that observation. And I think that's actually still an important, I think that's still an important problem certainly even in weather forecasting for a few days, and it's certainly a problem when we're assimilating observations into sort of climate models to do perhaps decadal or multi-decadal forecasting. And better assimilation will mean better reanalysis products. We heard in the last talk about reanalysis. That's an important tool these days. So that goes without saying. And actually, if we have better higher resolution models, I think we'll do a better job at trying to parameterize lower resolution models as well. So we heard about Destination Earth, Destiny as it's shortened to, which is an EU project funded under Digital Europe. So sadly, the UK has is not a member of this project, but the main feature of it is to develop kilometre scale models. But there is a problem, which is that we do need exascale computing, and indeed the first exascale computer, exaflop computer, now exists in Oak Ridge, the Frontier computer. But currently, the way things work is that in the coming few years, I'm sure we in Europe will start to get them. But these will be seen as general purpose. I mean, there may be specific machines dedicated to national security and nuclear weapon testing and that sort of thing. But from a general point of view, the scientists will share access. And this is really no good for this type of climate problem. We need dedicated exascale computing. We argue that the climate problem is as important as nuclear weapons testing or national security. I've sort of called for a CERN for climate change for a number of years. With my colleagues, led by Julius Slingo, who is the previous chief scientist of the Met Office, we've kind of reiterated that call in a recent Nature climate change paper. Now, if you do the sums, even with exascale computing, you're still struggling, and I think Joel again pointed this out, if you're envisaging multi-decadal ensemble integrations. So the question is, in parallel with all these kind of high-profile sort of ideas of trying to get dedicated exaflop computing, can we simultaneously improve the computational efficiency of our models so that when these resources really do become available, which I hope will happen at some stage, then we'll be in a good position to really do these kind of runs out to 2080 or something, maybe 50 years into the future. So I just want to spend a few minutes talking about computational efficiency. Just to remind you, we're solving an equation. We project the PDE onto some grid or spherical harmonic basis in the case of ECMWF, and then we represent everything unresolved by formulae, simple empirical formulae. Except actually they're not necessarily that simple. I think at ECMWF, which is primarily a weather forecasting center, these parameterizations can take up to half the total compute time of running a model. And in a climate center where people have additional so-called Earth system complexity, which would include biosphere mechanisms, cryosphere mechanisms, chemistry, and so on. One is often talking about the right-hand side as being the dominant part, actually, of the overall cost, maybe up to 70 or 80%. But one has to remember that the right-hand side is basically a set of semi-empirical formulae. The left-hand side is the proper laws of physics. I've put in the point that these days, certainly in numerical weather prediction, it sort of recognizes actually one of the figures that Joel showed about turbulence. There's a certain scale invariance to turbulence. So when you look at turbulence in his, whatever it was, porridge or something, I can't remember what it was now, some little sort of thing bubbling away, and then looking at in the large scale climate system, you get similar patterns. But in climate models or weather prediction models, we very much violate that scaling invariance by putting a hard truncation limit, and stochastic parameterization tries to at least smear that out, so representing the right-hand side, not by sort of formulae, but stochastic formulae. So we touched on this a little bit already in these talks. How can AI try and speed up this type of process? Well, one idea could be you pretty much replace everything. You run the model out, you run it over the 20th century, and then you get some AI system to emulate it, and you use that to somehow make your projections out to whatever it is, mid-century or beyond. So I call that kind of hard AI. We're sort of using either observations or model output to sort of produce some very highly sort of computationally reduced system. I'm deeply skeptical about such an idea, and I just want to give you an example of something that I'm working on with some colleagues in Oxford, which is the flooding which occurred in Pakistan this year. Which everybody has come out and said, yeah, that's clearly caused by climate change. Even the minister for Pakistan, the environment minister, said it was. And there's been a report by the World Weather Attribution Group saying that climate change contributed to it. Now, the problem is that if you so we've been doing some studies of this Pakistan heat wave based on seasonal forecasts, and we've rerun the forecasts with a reduced amount of carbon dioxide, and indeed the amount of rain that's forecast over Pakistan goes down by about 20%. So from that point of view, yes, indeed, this year's flooding in Pakistan, the floods were exacerbated by climate change, probably to the tune of about 20% of the rainfall. The interesting thing is we've also done some sort of seasonal forecasts with the same initial conditions, but increasing carbon dioxide to maybe what it will be towards the end of this century. And the interesting thing is that then the rainfall also decreases. So it's a very non-monotonic behavior. So what's going on? What's basically going on is that right now we're in a kind of early phase of climate change where most of the effects can be understood thermodynamically. So you have a monsoon flow, you add CO2, that warms the atmosphere holds more water. This is just, O-level physics, GCSE physics, isn't it? And it rains more, and that's kind of what happens, and that's what a lot of the models show. And if you were to train an AI system on, what's happened in the last 50 years with climate change, that's what it would come up with. It would come up with the thermodynamic response to climate change. But as we go into the future, we will start to see climate change affecting the dynamics of the coupled ocean-atmosphere system. So, in particular, this year, although climate change exacerbated rainfall over Pakistan, it was not the major driver of rainfall over Pakistan. The major driver was the El Nino, which is in its opposite, in its negative La Nina phase. It's been like that for the last two years. We're coming up to 3 years of a long-lived La Nina event. And it's kind of well known that La Ninas tend to be associated with strong monsoons. So to understand the long-term likelihood of flooding in Pakistan, you have to understand how does CO2, increasing CO2 in the atmosphere, change the probability of an El Nino or a La Nina event. There's no way you're going to get that from looking at past data or indeed from a simulation of a model over the 20th century, because it's not being driven in that regime where the CO2 has gone up so much it's affecting the dynamics of the coupled ocean-atmosphere system. So I think there's a real danger that, asking an AI system to extrapolate from a current data or from a current simulation of current climate into the future, when there are important dynamical processes which will start to become apparent in the future, but are not apparent now. So for that reason, I'm really skeptical about kind of AI as a sort of panacea for just kind of removing all this computational complexity. So there's a kind of a medium, what I call, so these are three sort of hard to soft. There's a medium AI. So I'm kind of skeptical about hard AI. This is the medium one I'm kind of agnostic about. There are groups doing it, and we'll see how it goes. I'm not sure. I think the jury's out. Which is basically this idea: can you derive better parameterizations than we currently have, just by letting the AI free on say a 1 kilometer scale simulation over the 20th century or whatever? Can it learn parameterizations better than us humans have been able to derive them ourselves? And as I say, I'm kind of fairly agnostic about that. It may be we can, it may be we can't, I don't know. But one thing that I think is a pretty much or should be guaranteed, or at least I'm certainly enthusiastic about it, and I don't see any major objections, is what I call soft AI, which is you take the current parameterizations, for example, in the atmosphere, long-wave radiation is a very expensive part of the parameterization scheme. You could imagine doing it on chemistry and all sorts of things like that. And what you get the AI to do is to learn the parameterizations themselves. And the idea is, hopefully, if everything is just based on matrix type of algebra, you can do it at relatively low numerical precision, maybe down as far as 16 bits. I'm a great believer in that there's considerable scope for reducing the numerical precision of our models. We've already shown it very categorically that we don't need 64 bits. ECMWF has moved to 32 bits recently, and that's quite adequate. And I think there's a lot of scope for further reduction. So the idea there would be not the AI is learning new physics, but it's doing the physics much faster. And that's part of the sort of rationale of using it to improve the computational efficiency of code, which is going to be important when we get to run these kilometer scale models on exascale machines. So I just got like a couple of slides. So I just want to say one other thing about AI in a kind of related but slightly different context. But again, this relates to adaptation, climate adaptation, but it's about the specific issue of improved early warning systems. So I think most disaster relief and humanitarian agencies recognize that part of the adaptation program, particularly for developing countries, is to provide them with better and more timely early warning systems for particular instances of extreme weather, so they become more resilient. And there is a fantastic program now around the world, which is really changing the whole paradigm of how disaster relief organizations operate, which is called anticipatory action. So you only have to go back a few years, and you would get some event which would devastate a region. Could be a tropical cyclone or potentially actually a drought, a long-term drought. And the agencies would only start to react after the event had passed and everything was devastated, and then it's really horrible because the roads are down, the transportation's down, and people are desperate for food and shelter and water and medicine and so on and so forth. So the idea here is that they're developing programs where you can take precautionary action, anticipatory action. And this is one actually of the applications of ensemble forecasting, because they need criteria for determining when the event has a high enough probability that it can justify taking precautionary action, because all of these agencies have limited funds. You know, they don't have infinite funds to go in every time there's a slightest possibility of an extreme event. This anticipatory action is becoming quite an important kind of development in this sort of interaction between operational weather prediction centres and humanitarian and disaster relief agencies. But the problem, again, is that with current resolutions and with weather forecast models, we are down to around 10 kilometres grid spacing. But even still, some of the intensities of rainfall, because often, you know, one is talking about vents which might be 15 sigma. It's not like 2 or 3 sigma. These are massively out on the tails, the things that kill people. So can we do better at really predicting the intensity of events, you know, right down at a like 100-meter postcode type scale? Now, NWP centres around the world, numerical weather prediction centres around the world, they do have this program of trying to downscale the global models, so they may get output from ECMWF, for example, but then to try to get from the 10-kilometre grid down to 1 kilometre, they would have a regional model where they would feed the data, the forecast data, in as lateral boundary conditions. But there are real problems with this approach, which I wrote about in I haven't actually published this paper, but it's you can get it on the World Meteorological Organization website if you're interested. Which is that, and by the way, you might say, well, all right, sorry, I'll come to this point in a minute. But, so the problem with it is that particularly a developing country Met Service can only afford to run their limited area model, you know, maybe for a couple of days into the future. And they can't afford to run like all 50 members of the ensemble downscaled. So they may have like half a dozen at most ensemble members run out for a couple of days. But what these agencies want to know, if they're going to get medicine and food and shelter and stuff in place, they want to know a week before or 10 days before, so they can start to get the stuff to the airports, they can start to load it on the planes and blah, blah, blah. So having it a couple of days before is pretty useless. Not useless, but it's certainly not optimal. You might say, well, maybe these agencies could bypass the limited area models, just base their analysis on the global ensemble. But there's a lot of politics here. If a country is going, if an agency is going into a country providing, food and shelter and so on, they have to be working with the government, and the government is going to insist that they use the Met Service's forecast data rather than, say, some global provider, just for sort of internal political reasons. Okay, so the idea is that maybe there's an alternative here, that the Met Services could develop their own highly specific AI schemes for doing this downscaling. Because a lot of the downscaling is actually fairly deterministic. Again, if you think about a mountain, if you don't have the mountain well represented in your global model, then, for example, you wouldn't get the intensity. If you have some system that's approaching the mountain chain, you would under-simulate the intensity of rain on the upslope, and you would over-predict the intensity of rain on the downslope. Similarly, if there was a kind of a complicated, land-sea boundary, you might misrepresent. You would misrepresent some of the effects of that boundary. So this is, again, a second application of AI to do the downscaling. So you're going from a relatively coarse scale to a relatively fine scale. So it's not a deterministic map. This would be some kind of one-to-many, effectively stochastic map. But the global models are ensembles anyway, so you're producing like super ensembles. And of course, the advantage of this would be, so there are two advantages. One is you would produce big ensembles. You wouldn't be just using 5-member ensembles. And also the scheme would go out for the full range of the ECMWF forecast, say 2 weeks into the future. So it's going to be much more useful for the agencies. And just the last thing, if any director of a Met Service is watching this program. One great advantage of this scheme is it gives you a reason for maintaining your local observational network. If you've got radar systems or local rain gauges and you want some reason to keep these funded, this is actually a really good reason for doing that. Because otherwise it's really difficult, because local radar and rain gauges things don't actually feature greatly in the overall assimilation of information into a global weather forecast. That's much more dominated by satellite technology. Okay, so actually so those are two important areas. As I say, Matt will, after lunch, will kind of pick up with showing some specific examples of this in practice. So this is just very much an introductory talk to that. Thank you.
Thank you very much. Do we have questions? Oh, there is an online question. Okay.
So there's one online. Got a lot of acronyms in, so hopefully you know what these are about. So this is from Yevgeny from the National Oceanography Centre. So this question is, the carbon removal scenarios, CDR, MIPs, ZEC, MIPs, provide an assessment what may happen in different emission reduction pathways. Do you think we need more of these rather than go for a higher resolution? Do we have enough evidence from the high resolution versus low resolution MIPs to distinguish between different climate trajectories? My impression from SIMIP, which is Sea Ice MIP for CMI P6 IPCC, is that the low 1 degree and high res quarter degree model perform the same?
Yes, but the problem is we're not talking about a kind of like a linear improve or linear reduction in error as the resolution improves. I mentioned that once you get down to a kilometre or so, you can start to resolve, which basically resolve means represent with the laws of physics, processes which are otherwise parameterized. So CMIP, there are indeed some, CMIP has a range of resolutions. Perhaps a typical resolution is around 100 kilometers, but there are a few that get down to sort of 20 or so kilometers. And you still, at 20 kilometers, you still need to parameterize deep convective clouds, ocean mesoscale eddies, orographic gravity wave drag. So you haven't reached that kind of quantum jump downwards, if you like, where you're suddenly no longer parameterizing these things. So we won't see those benefits. 20 kilometers gives you some benefit from being able to resolve topography better, but it's not giving you the benefit of being able to replace these empirical parameterizations with the laws of physics. So you can't really deduce anything, I don't think, from a 20 kilometer run about what you will expect to see with a 1 kilometer run. Yeah.
Thanks, Tim, for your very interesting overview. My question is about, instead of going in the direction of making global predictions in a number of years and so on, is there any work in the direction of identifying early precursors of extreme events? So rather than trying to predict the flood in Pakistan in 10 years' time, identifying the conditions that might tell you with some advance that an extreme event is going to happen in some region.
On what time scale are you talking about now?
Yeah, in any suitable time scale, they would provide some early.
Well, I mean, there are people who study. I mentioned El Nino and La Nina. There's quite a wealth of evidence about the changing likelihood of extreme events in one particular region during El Nino or La Nina years. So And, you know, La Nina and El Nino, although we tend to use coupled ocean atmosphere models to do the predictions. I mean, you can actually do, you can develop purely statistical models to predict El Nino on timescales of a few months, and they do reasonably well, actually. So, you know, in some sense, you can, you know, I mean, I guess the reason for wanting to develop the coupled models is that you can do better than these statistical schemes, but nevertheless, you can do something that's useful and credible with just purely statistical schemes. So you could say, yeah, I mean, from your if you have precursors of the either El Nino or La Nina, you could infer from that the likelihood of extreme event. It could be extreme rainfall over Australia, for example, during a La Nina, or extreme drought over California during a La Nina. But what I'm saying is that, you know, the climate change problem, as it will unfold in the coming decades, is going to be about how climate change affects these El Nino and La Nina events. What's the probability, how's the probability distribution of these things changing? You know, I'm sure a lot of people think around the world that these droughts and fires in California are, you know, that's it, that's climate change, that's what we're stuck for the next 100 years or 1,000 years or something. But it really depends on what El Nino does. If we go into, you know, we just don't know, and the models totally disagree on this, how increasing levels of CO2 change the PDF of the El Nino event. And if this 3 or 4 years of La Nina is just a rather transient phase, and actually the long-term effect of CO2 is actually to make El Nino, so where the Pacific, the East and Central Pacific is warmer than average rather than cooler than average as it is at the moment, then the climate of California would be completely different to what it is today. It'd be wetter. So this is like an order one question for anybody thinking seriously about investing in infrastructure for the long haul at a regional level. And that's why I think, you know, funding a CERN for climate change is a complete no-brainer, because it's so cheap compared to the actual implications of the expenditure that governments around the world will be making on adaptation, which would be in the trillions, whereas this is just a kind of couple of $100 million a year, which is peanuts.
Yeah, Tim, thanks for sharing really interesting talk, and the climate physics and how we represent it is clearly really important. And it seems like we're really at the edge, or no, at the buffers of our computing capacity, what we can do. So thinking about the development of computing over the past decades, and we're coming up to hopefully a quantum computing paradigm, is there any work to do with what sort of algorithms can be used to solve these problems in a quantum computing setup, so multi-state processes?
I've written a paper with a colleague of mine on quantum computing for weather and climate, and we're waiting, we've submitted it to the bulletin of the American Meteorological Society, and we're hoping it'll be accepted. Quantum computers are not going to be a panacea for, you know, some exponentially faster integration time, though they may have a role in rather sort of specialized niche parts of the code. And the problem comes, I don't want to sort of go into a lecture on this now, but the problem comes when, I mean, the good part about quantum computers is that with a relatively small number of qubits, the basic elements of a quantum computer, the qubit, which is the superposition of like an up and a down state of an atom or an electron or photon or something. We know from quantum theory that the state space increases exponentially as you entangle more of these qubits together. So with 30 qubits, you can entangle the state space of a 30-dimensional qubit system is about 1 billion. So you can represent the state space of a weather forecast model with 30 qubits. That's really good. The problem is, at the end, you do all your unitary manipulations, which is basically you encode the equations into a sort of quantum system. I hope that's not me. But at the end of the day, you have to measure these qubits. And that's something that people tend to neglect. And if you've only got 30 qubits, you've only got 30 measurements, and these measurements give you a yes or no answer. So it's like you want to know everything about the state of the weather, but you're only allowed to ask the model 30 questions. And that's completely hopeless because, global models, as somebody was saying, Joel was saying, there's lots of information you want from those integrations. You don't want just 30 yes, no. So that for me is almost a showstopper for quantum computing as a replacement for classical computers. But there may be, as I say, there may be niche areas where they can accelerate code. For example, if you're just wanting literally a yes or a no from some piece of code, true or false or something, then yeah, they could maybe do that really, really fast. But it's not a panacea, no.
Thank you very much. I think I will speak again. And, well, we're kind of running late. Well, we are supposed to start in half an hour, I don't know. Well, let's start at 2. Yeah, it would be. Yeah. Okay. So do we have lunch outside? Yeah. Thank you very much.
Oh, yeah, sorry.